By 2050, humanity will face a choice: remain a one-planet species doomed by the next asteroid, supervolcano, or global catastrophe, or become a two-planet civilization. And Mars, whether we like it or not, is our insurance policy. The countdown has already begun. There is a profound moment in human history when imagination transforms into engineering, when the impossible becomes nothing more than a challenge of time, resources, and creativity. That moment is now unfolding before our eyes as we prepare for the greatest migration our species has ever attempted. Long before the first footprint presses into the ochre dust of Mars, an army of silent pioneers will already be their robot, autonomous systems, artificial intelligences operating tirelessly in the frigid twilight of a distant world. These machines will not simply gather data, they will be the architects of a new branch of civilization. The idea seems almost mythic, but it is grounded in cold, precise technology that already exists. The first wave of these explorers will be designed to construct the foundations of human life in an environment so hostile that even a minor oversight could mean instant disaster. Yet, unlike humans, they do not fear radiation. They do not breathe oxygen. They do not complain about the cold. They function tirelessly with no need for food, water, or rest. They are the ideal settlers for a world as unforgiving as Mars. These robotic pioneers will land with the explicit purpose of creating an infrastructure that allows humans to survive from the moment they arrive. Imagine vast fields of solar arrays unfolding automatically across the red plains panel, orienting themselves optimally to capture every fragile photon from the faint Martian sun. Picture robotic crawlers digging trenches that will become the underlayer of power cables, communication lines, and water recycling pipes. Visualize massive 3D printing rovers extruding into existence the first shelters, domes, tunnels, radiation shields, and storage facilities built not from imported materials but from the Martian regolith itself. This regolith, a powdery mixture of basaltic rock, iron oxide, and minerals, can be fused into ceramic-like structures using microwaves or lasers. What appears as barren sand becomes, through technology, the building blocks of a new civilization. And this is only the beginning. Robotics on Mars will operate as a complete ecosystem, rovers repairing other rovers, AI supervisors orchestrating fleet of machines, autonomous power stations, diagnosing their own faults, and adjusting load distribution across the colony. The robots will map the terrain in exquisite detail, identify optimal regions for future expansion, locate ice deposits critical for life support, and even create emergency shelters for incoming astronauts. In the freezing isolation of a world with no breathable air and temperatures that can plunge far below minus 100 degrees Celsius, these machines will transform a dead planet into an environment that humankind can metaphorically inhale. Without them, human presence on Mars is not merely risky, it is impossible. But the role of these robots goes far beyond laying the groundwork. They represent a philosophical shift in the way humanity approaches exploration. For thousands of years, exploration meant risking human life on the frontier. Now, we send emissaries that do not fear the unknown. They touch danger so that we don't have to. They experiment with the chemistry of Martian soil, test the strength of new structures, and prepare living spaces with a precision no human hands could match in such harsh conditions. The result is not simply a base, it is a launch pad for the next phase of evolution. Once these mechanical pioneers have prepared the landing sites, built initial habitat, and tested every system hundreds of times, only then will the first humans arrive. They will step out of their spacecraft not into barren land, but into a prepared outpost, a place where the lights are already on, the air is already breathable, and the first traces of a new society have already taken root. And these structures themselves, these habitats rising from the Martian dust, represent one of the most extraordinary revolutions in modern engineering, the ability to build entire cities using 3D printing technology. On Earth, construction requires armies of workers, heavy machinery, tons of materials, transported from around the world, an enormous logistical complexity. On Mars, none of this is possible. Every kilogram of material launched from Earth costs a small fortune. Every human exposed to construction risks is a potential tragedy. The only viable solution is to bring the machines, let them harvest the land, and allow them to print the structures of the future directly from the soil beneath their treads. And it turns out that Martian soil, once considered merely a dusty nuisance, is the perfect material for constructing durable shelters. By heating the regolith with microwave beams, 3D printers can fuse the particles into a solid, stone-like material, creating blocks, arches, beams, and even entire rooms layer by layer. The process is elegant, efficient, and incredibly resilient in a place where storms, radiation, and extreme temperatures test every design. Imagine walking through one of these first Martian cities. The walls, curved for structural strength, gleam with a glassy finish formed by the fusion process. Translucent panels allow muted sunlight to filter through. Networks of cables pulse with energy. Under the floor, life support systems hum gently, extracting oxygen from ice, deposits and recycling every drop of water with almost perfect efficiency. These printed habitats will not be small outposts like the research bases in Antarctica. They will expand into multi-level structures interconnected through tunnels and pressurized walkways, forming entire district science labs, living quarters, greenhouses, medical bays, and eventually cultural centers. The technology allows for structures taller than any human could build manually on Mars. Because the printers do not tire, do not lose precision, and do not fear the elements. Every curve can be optimized for protection against radiation, maximizing internal space while minimizing wasted material. The printers can work continuously, producing new layers during the night when humans are asleep, gradually forming the skeleton of a new civilization while the stars drift silently overhead. This method of construction also solves one of the most daunting challenges of Mars: radiation. Unlike Earth, Mars has a weak magnetic field and thin atmosphere, providing little shielding against cosmic rays. Traditional construction using metal or imported materials would be expensive and insufficient. But by printing structures with thick, regolith-based walls, the colony gains natural protection derived from the planet itself. The buildings become extensions of Mars, grown rather than assembled, fused rather than bolted. As technology advances, some structures may even incorporate transparent aluminum or advanced polymers, allowing windows large enough to view the crimson landscape without sacrificing safety. As the colony grows, new printers will construct greenhouses with reinforced glass and insulated frames, creating oases of greenery where fruits, vegetables, and oxygen-producing plants thrive. Over time, these greenhouses will evolve into vast agricultural domes, allowing settlers to produce their own food with increasing independence from Earth. Imagine fields of engineered crops under artificial lights, robotic pollinators drifting between blossoms in slow, graceful paths, and autonomous irrigation systems, recycling every molecule of water with near-perfect efficiency. This is not a fantasy. It is the logical extension of technologies already tested on Earth and in orbit. The beauty of 3D printing on Mars is that it allows exponential growth. After building the first habitats, the printers will print more printers. After constructing the first district, they will construct factories. Slowly, methodically, the colony will expand from a cluster of buildings into a small town, from a town into a city. Each structure will carry the imprint of computational optimization curve, designed to distribute stress, reinforced edges that withstand dust storms, and interior designs tailored for human comfort in a world so alien that even the horizon looks different. And as these cities expand, a new psychological reality will take hold for human settlers. No longer will Mars feel like an outpost or an experiment. It will feel like home. Streets carved from fused Martian stone will create a sense of place. Public domes filled with oxygen-rich air will echo with laughter, music, and conversation. Underground transit tunnels will hum as automated shuttles glide silently through them. The colony will live, breathe, and grow like any other city except for the rail. Dust outside the walls and the faint sunlight filtering through the thin sky. These robotic pioneers and printed cities represent something far greater than engineering. They embody the idea that human destiny is not limited to one world. Each brick printed from Martian soil is a declaration that life is not confined to Earth. Every robotic rover moving across the plains is a symbol of our determination to survive, adapt, and expand beyond the cradle of our civilization. The first robots will lay the foundations. The first 3D printed shelters will shape the skyline of a world that has never known life. And from those beginnings will rise the first great interplanetary society built not by mythic heroes but by the relentless logic of science and the quiet unceasing work of machines preparing the future for their human creators. The next great chapter of our cosmic journey begins when we understand that Mars is not simply another planet. It is a time capsule of Earth's own distant past. As we peer into the iron-red sands of this frozen desert world, we begin to uncover secrets, billions of years-old secrets that hint that Mars might once have been warm, wet, and astonishingly Earth-like. This revelation alone reshapes everything. Mars is not the alien world we imagined. Mars is the cousin world we lost track of in the vast family tree of the solar system. And this relationship becomes the foundation for the technological leaps required to transform Mars into a place where humans can live, work, and build a new civilization. To comprehend how we might terraform Mars or recreate Earth-like conditions there, we must first decode its climatic history. Today, Mars is cold enough to freeze carbon dioxide right out of the atmosphere. But in the past, it likely had rivers that carved serpents. Like channels across its surface, lakes that shimmered under a rosy sky, and perhaps even oceans that lapped against ancient shorelines. These are not fantasies. They are written into the crust itself. Satellite images show dried river deltas. Rovers have discovered rounded pebbles sculpted by flowing water. Minerals that only form in warm, liquid conditions lie scattered across its plains. All of this evidence tells us that the Mars of today is the skeleton of a world that once lived a richer life. The collapse of Mars' magnetic field changed everything. Without a magnetic shield, the solar wind stripped away its atmosphere like a thief in the night. Over millions of years, Mars became the frozen wasteland we see now. But here lies the extraordinary implication if we understand how Mars lost its habitability. Then we can understand how to restore portions of it. No one is rebuilding the entire Martian environment. It would take centuries or more. But what we can do is engineer pockets, bubbles, and controlled habitats that mimic the conditions Earth naturally provides. This is the real beginning of colonization. Before we build cities under domes, we first build environments that let us live long enough to build anything at all. This is why the study of Martian geology and atmosphere becomes so crucial. Dust storms that can engulf the entire planet tell us how finely powdered the soil is, how easily it moves, how quickly it suffocates anything left unprotected. Its thin atmosphere teaches us how to harvest carbon dioxide and convert it into oxygen or methane. The permafrost ice hiding beneath the soil becomes our most valuable resource. With it, we can produce water, split that water into hydrogen and oxygen, and use these building blocks for fuel, breathing, and agriculture. Mars is a harsh planet, yes, but it is also surprisingly generous. It offers us what it can. Our job is to use deep scientific insight to unlock it. Understanding this past is not merely an academic exercise. It is the blueprint for the future. When we know what Mars used to be and what physical laws shaped its evolution, we can design technologies that align with those laws rather than fight them. That is how we transform a hostile world into a second home. And this brings us to the next stage, the technologies that will allow us to survive long enough on Mars to build the civilization we dream of. Every great migration in human history has been powered by the tools of its time, and the migration to Mars will be no exception. But unlike the settlers of old who crossed oceans using wood and canvas, our journey will be fueled by the most advanced engineering in human existence. We stand on the threshold of innovations that would have been mistaken for magic only decades ago. Rocket technology is undergoing a revolution driven by rapid reusability that slashes costs and makes interplanetary travel not merely possible, but routine. Instead of billion-dollar disposable rockets, we now envision fleets armadas of spacecraft, ferrying people and cargo back and forth like airlines crossing continents. And so, the backbone of our Martian future will be heavy-lift rockets capable of carrying tens of tons of equipment in a single launch. These machines are not just transportation. They are the arteries and veins of a new civilization, carrying life from Earth into the void. Advances in propulsion, such as methane-based engines, will allow us to refuel on Mars using the very resources buried beneath its soil. This means our rockets don't have to carry the return fuel from Earth, saving massive amounts of space and energy. This one innovation alone changes the economics of space travel forever. Life support systems will undergo a transformation equally dramatic. On Earth, air and water are free gifts of nature. On Mars, they become engineering challenges of the highest order. That is why scientists are developing regenerative life support cycles ecosystems in miniature that recycle every drop of water, every molecule of oxygen, every scrap of organic material. These systems imitate nature's elegance, but they must operate with the precision of a machine. In the tight, controlled environment of a Martian habitat, even a small failure can be catastrophic. The astonishing part is that each of these innovations begins teaching us something profound about Earth. 2. If we can recycle nearly everything on Mars, we can drastically reduce waste on our own planet. Energy will be the currency of survival. On Earth, the sun delivers abundant energy daily. But on Mars, the sunlight is both weaker and interrupted by planet-wide dust storms that can last for months. Relying solely on solar power would be like relying on a candle to light a stadium. So we turn to compact, nuclear reactors machines no larger than a shipping container that can power an entire outpost with steady, reliable energy through night, storm, and winter. With this energy we heat habitats, produce water, grow crops, and run life support systems. These reactors represent the beating heart of human survival on Mars. They mark the turning point from exploration to habitation. But even these technologies are only the beginning. The most ambitious innovations lie in construction technology. Traditional building methods are useless on Mars. We cannot bring cement mixers or steel beams from Earth. Instead, we turn to robotics and 3D printing using local materials. Imagine machines that scoop Martian regolith and sinter it into solid blocks, layer by layer, creating radiation-shielded structures. These autonomous builders will construct habitats before humans even arrive, laying the foundation for the first Martian neighborhood. This is the profound shift. Instead of carrying civilization to Mars, we will manufacture civilization on Mars. With local materials, local energy, and local chemistry, we begin creating a self-sustaining presence that no longer depends entirely on Earth. This moment, the moment when Mars no longer needs constant supply shipment, is the milestone that transforms a dusty outpost into a genuine colony. And through all of this, one truth becomes increasingly clear: colonizing Mars is not simply a matter of engineering, but a vision. We are not merely transporting humans to another planet. We are expanding the stage upon which the drama of human life unfolds. The technologies we develop will rewrite our relationship with the cosmos and redefine what it means to be a multi-planet species. We are on the brink of becoming participants in the oldest story of all, the story of life surviving against all odds by embracing curiosity, ingenuity, and the courage to explore. As humanity prepares for its greatest migration, one of the most profound questions emerges. How will we feed ourselves on a planet where nothing naturally grows? Mars, with its thin atmosphere, frigid temperatures, and soil laced with toxic perchlorates, offers no fertile fields, no gentle rain, no comforting blue skies. Yet this is precisely where the genius of human innovation shines brightest. Throughout history, whenever nature presented a barrier, we invented a tool to overcome it. On Mars, we will do the same, transforming barren landscapes into controlled oases of life. The key to this transformation is closed-loop, high-efficiency agriculture farms unlike any ever seen on Earth. Imagine vast greenhouses pressurized like aircraft cabins, shimmering under the soft glow of artificial sunlight tuned to optimize photosynthesis. Within these sealed sanctuaries, crops will grow in nutrient-rich solution rather than soil, eliminating the need to process Martian dirt. Hydroponics and aeroponics will allow lettuce, potatoes, wheat, and even fruit trees to flourish, not because Mars supports them, but because human intelligence recreates the conditions they need to survive. Every drop of water will be recycled. Every molecule of carbon dioxide will be captured and reused, and waste will be converted into fertilizer through microbial alchemy. The remarkable part is that plants will do more than simply feed us. They will become living engines of life support, converting exhaled carbon dioxide into life-giving oxygen. This is the elegance of nature. A single leaf carries out chemical reactions that would require factories on Earth. On Mars, the quiet work of photosynthesis becomes sacred. Astronauts will walk through humid rows of green, not only to farm but to breathe, to restore their psychological connection to life, to touch something familiar in an unfamiliar world. Yet greenhouses alone cannot feed an entire colony. That is where modular food systems come into play. Microfarms that produce algae, yeast, fungi, and protein-rich plants, on a scale far smaller than traditional agriculture. These systems are compact, efficient, and astonishingly productive. A single bioreactor the size of a refrigerator could provide the nutritional equivalent of acres of farmland. Algae, for example, grow with incredible speed, converting sunlight or artificial light directly into protein. And oils. Although such foods might not resemble the meals we are used to today, they will ensure survival and provide essential nutrition in the early decades of colonization. Advanced genetic engineering will also play a crucial role. Plants adapted to Earth's warm, oxygen-rich environment struggle under Martian conditions, but with modern biotechnology we can enhance their resilience, enabling them to thrive under lower pressures, reduced light, or fluctuating temperatures. Crops could be modified to grow faster, use less water, tolerate higher levels of radiation, or synthesize vitamins essential for long-term survival. Mars will become the greatest laboratory for agricultural science ever conceived, forcing us to think beyond traditional farming and embrace a new form of planetary cultivation. The astonishing implication is that feeding a Mars colony will transform agriculture on Earth as well. Techniques developed for extreme environments will help us grow food in deserts, drought zones, and regions ravaged by climate change. Mars becomes a test bed for the most efficient farming systems ever invented, systems that could eradicate hunger on Earth. In this sense, the journey to Mars is not an escape from our home planet, it is a way to save it. But producing food is only part of the puzzle. The next challenge is building the physical backbone of a Martian civilization, habitats, laboratories, factories, and protective structures that shield humans from radiation, temperature swings, and micrometeorites. Mars demands construction techniques that would look impossible on Earth, yet they will become routine on the red planet. The extraordinary opportunity is that Mars is rich in raw materials if we know how to use them. The soil itself, composed of iron-rich regolith, becomes the foundation of construction. Instead of transporting heavy building materials from Earth, we will turn Martian dust into bricks, tiles, and structural components through 3D printing. High-powered lasers or microwaves can fuse the regolith into solid stone, creating radiation-proof walls thicker and stronger than concrete. Entire habitats can be printed layer by layer using robots that tirelessly build even in the harshest weather conditions. This shifts construction from a labor-intensive human task to a largely automated process. The first wave of robotic builders will arrive before humans, constructing shelters, landing pads, and supply storage facilities. When settlers step onto Martian soil, they will enter structures already shaped by autonomous machines that work without rest, without fear, and without requiring life support. These robots will be the true pioneers, claiming the landscape and preparing it for human life. Over time, they will expand their capabilities, transitioning from simple construction to complex manufacturing. They will smelt metals, refine minerals, and produce the components needed for machinery, tools, and future spacecraft. Underground habitats will also play a crucial role. Mars is riddled with lava tubes, massive tunnels carved by ancient volcanic activity. These natural caverns offer unparalleled protection from radiation and provide stable temperatures year-round. By sealing and pressurizing these tunnels, entire communities can be built safely beneath the surface. Imagine vast subterranean cities lit by warm artificial suns with parks, lakes, and neighborhoods stretching through gently curving corridors. Humanity's first permanent foothold on another world may begin in the darkness, where the planet itself becomes our shield. To support this growing ecosystem of construction and habitation, new materials must be engineered specifically for Martian conditions. Metals produced on Mars will have different properties than their Earth-based counterparts, shaped by local chemistry and gravity. Polymers and composites will be designed to withstand extreme temperature swings. Transparent aluminum-like materials will create windows that resist radiation while allowing sunlight into greenhouses. The science of materials will experience a renaissance as we learn to craft the building blocks of civilization from alien soil. Energy again becomes the lifeblood of construction. Solar arrays will stretch across the plains, soaking up every available photon. Nuclear reactors will hum quietly, powering factories and life support systems. Eventually, we may tap geothermal heat from beneath Mars' crust, unlocking another renewable energy source. With abundant energy, Martian industry becomes not only possible but scalable. We will produce steel, ceramics, plastics, and glass, all without relying on Earth. This independence marks a pivotal moment in colonization, the transition from an output, living on resupply missions to a self-reliant civilization charting its own destiny. Infrastructure will expand rapidly once the tools of local manufacturing and construction take hold. Roads will cut through dusty landscapes, connecting research centers, mining sites, landing zones, and residential hubs. Transportation vehicles will glide across the surface on pressurized wheels or hover using low-atmosphere lift systems. Eventually, high-speed tunnels could link major settlements, enabling rapid movement across vast distances. Every new structure, every road, every greenhouse becomes a symbol of humanity's ability to adapt, innovate, and shape a world that once seemed impossibly inhospitable. This phase where agriculture and construction intertwine marks the true birth of a Martian society. Food, shelter, and energy form the three pillars upon which all civilizations are built. When these pillars stand strong on Mars, everything else becomes possible: education, culture, science, art, and eventually a fully functioning economy. Children may one day grow up never having seen Earth, learning instead about the pale blue dot in the sky as the ancestral homeland of their species. They will play in Martian parks, study Martian engineering, and dream of exploring other moons and planets. A new branch of humanity will emerge, molded by a world that challenges every aspect of human ingenuity. With the mastery of food production and construction, Mars transforms from an isolated expedition to a thriving frontier, igniting a new era of exploration and scientific discovery. Every greenhouse built, every habitat printed from dust, every crop grown beneath a forest sky carries the same message. Humanity was never meant to be confined to one world. We were born on Earth, but our destiny stretches across the stars. As the foundations of a Martian settlement begin to stabilize, a greater question emerges: how does a society millions of kilometers away remain connected to the cradle of humanity? Communication becomes the nervous system linking two worlds. On Earth, messages travel at the speed of light across fiber optic cables, bouncing between satellites and ground stations in fractions of a second. But Mars is far from this familiar network. Depending on orbital positions, a signal can take anywhere from 3 to 22 minutes to travel from one planet to the other. This delay reshapes everything from conversations to emergencies, from scientific coordination to emotional connection, forces humanity to rethink communication itself. For the first Martian settlers, every message sent home becomes a small time capsule, arriving not instantly, but with a noticeable pause. Loved ones will send video messages, knowing they will not receive an answer until much later. Scientists on Earth guiding robotic operations will build systems that predict human needs long before a response arrives. This distance compels us to design communication technologies that can function autonomously, intelligently, and reliably, even in isolation. Artificial intelligence evolves into the unseen operator, handling delays, filling gaps, and maintaining real-time operational awareness despite the unavoidable lag. To make this possible, a mesh of orbiting satellites will surround Mars, forming a miniature celestial internet. These satellites will relay signals across the Martian surface, connecting habitats, research sites, and rovers. They will eliminate blind spots created by mountains, craters, and dust storms. Orbital relays ensure that even if a settlement is on the far side of Mars, out of direct line of sight with Earth, the message will still find its way through a chain of satellites to its destination. Eventually, an interplanetary communication backbone will emerge, stretching between the two planets like a cosmic web of information. Laser-based communication systems, far more powerful than traditional radio waves, will become the cornerstone of this network. Lasers can transmit vast amounts of data with astonishing precision. Entire libraries worth of information can be sent with a single beam of light, tightly focused and resistant to interference. The challenge, however, is the thin Martian atmosphere and the ever-present dust, which can disrupt even the most concentrated beams. To counter this, adaptive optics will be used to correct distortions in real time, allowing laser communication to slice through dust storms with remarkable accuracy. As communication infrastructure expands, so will the reach of Martian society. Live broadcasts from the Red Planet may become commonplace. A simple sunrise over the Martian horizon, captured by a resident with a handheld device, could be streamed to classrooms on Earth with a slight delay. Children learning about the solar system could watch their distant cousins exploring canyons, and volcanoes unimaginable in scale. The psychological benefit of this interconnection cannot be overstated. It will remind Martian settlers that they are not isolated pioneers, but part of a civilization stretching across planets, bound by the same dreams and the same curiosity. Yet communication is only one part of creating a fully functional interplanetary culture. The next great leap comes when space becomes not merely a place we visit, but a domain we inhabit and explore freely. To achieve this, spacecraft must evolve from single-use machines into vehicles capable of repeated journeys, refueling, repairing, and relaunching entirely off Earth. The dream of becoming a multi-planet species depends on building a transportation system robust enough to bridge worlds the way ships once connected continents. The journey begins with reusable spacecraft that can take off from Earth, travel to Mars, and return with minimal refurbishment. But this is only the first step. True interplanetary mobility requires the ability to construct and maintain ships in space itself. The harsh gravitational pull of Earth consumes enormous amounts of fuel and resources, making it inefficient as a base for large-scale space construction. Mars, with its lower gravity and extensive mineral resources, offers a superior launching ground for deeper exploration into the solar system. Imagine shipyards floating in Martian orbit or anchored to the slopes of ancient volcanoes. Here, robotic arms and autonomous assemblers would build spacecraft. Piece by piece, forging hulls from metals mined on Mars, fabricating electronics from locally refined materials, and integrating propulsion systems designed to function in the vacuum of deep space. These vessels could carry settlers to the moons of Mars, such as Phobos and Deimos, which themselves may become hubs for mining and research. From there, humanity could push outward toward the asteroid belt home to trillions of dollars worth of minerals, and eventually toward Jupiter's moons or the icy oceans of Saturn's domain. This expansion is not merely technological. It is psychological. A species confined to one world behaves differently from one that inhabits many. When early humans left Africa, they encountered new terrains, new climates, and new challenges. Each migration expanded their understanding, reshaped their culture, and accelerated their development. Settling Mars will have the same effect on modern humanity. It will expand our perspective, stretch our imagination, and force us to innovate in ways that Earth alone could never demand. For the first time, children may grow up on two worlds simultaneously, learning that distance is not a barrier but an invitation. As interplanetary travel becomes easier, a new type of society will begin to form. A network of worlds connected by commerce, research, culture, and shared destiny. Mars may specialize in materials science and robotics, Earth in biological research and governance, and space-based colonies in energy production and manufacturing. This diversification mirrors the evolution of cities and nations on Earth, but on a cosmic scale. Even trade routes will emerge, not based on oceans or mountain passes, but orbital mechanics and gravitational slingshots. The economic map of the solar system will reflect the movement of spacecraft, mining of asteroids, and the distribution of scientific data across planets. In this grand vision, each world becomes a contributor to a larger civilization. Customs will evolve based on environmental realities. Martian art may celebrate landscapes of red canyons and blue sunsets, while Earth art continues to draw from oceans, forests, and life abundant. Martian architecture might emphasize domed habitats and underground cities, while Earth's remains rooted in skyscrapers and urban sprawl. Even time itself will diverge as Martians adapt to a day that is slightly longer than Earth's, reshaping the rhythm of work, rest, and culture. These differences will not divide humanity, they will enrich it. The true power of such expansion lies in what it represents: resilience. A civilization confined to a single planet is vulnerable to natural disaster, cosmic impacts, pandemics, and self-inflicted catastrophes. By spreading across worlds, humanity becomes far more durable. Knowledge, culture, and life itself will be distributed across multiple environments, ensuring continuity even when one world faces difficulty. This is not an escape from Earth, it is the greatest act of preservation ever conceived. Earth remains the heart of civilization, but Mars becomes its shield and its springboard. As the solar system begins to fill with the first sparks of human settlement, a remarkable transformation takes place. The night sky, once a place of mystery, becomes a highway of possibility. Each dot of light is no longer just a star but a destination, a future colony, or a stepping stone toward deeper understanding. Children born into this era will grow up believing that human presence is not restricted by geography or atmosphere, but defined by curiosity and courage. They will inherit a civilization that has already taken its first steps into the cosmos and be inspired to take the next. Mars becomes the frontier, not because it is easy, but because it challenges every assumption we hold about survival, innovation, and destiny. The ability to communicate across planets, to travel between worlds, and to build a society that spans the solar system is more than a technological achievement, is the beginning of humanity's next chapter. The leap from Earth to Mars is the hardest, but once it is made, the rest of the solar system opens like a series of unlocked doors. And beyond that, the stars themselves become invitations, whispering to future generations that the universe is vast, welcoming, and waiting for them to explore it. In the end, the journey to Mars is far more than a technological challenge or a scientific experiment. It is the next great chapter in the story of our species. For countless generations, humanity has looked up at the night sky and wondered what lies beyond the shimmering veil of stars. Now, for the first time in history, we are not simply dreaming, we are becoming participants in that cosmic drama. The decisions we make today, the technologies we build, and the courage we summon will determine whether we remain a one-planet civilization or step into the vast theaters of the universe as pioneers of an interplanetary future. Mars represents the testing ground for our greatest ambitions. It challenges us to rethink life, biology, engineering, society, and even what it means to be human. By learning to grow food on barren soil, build cities under alien skies, and communicate across millions of miles, we transform ourselves into a species capable of surviving anywhere. And when that transformation begins, the solar system itself becomes our backyard. Children born decades from now may take field trips to Martian valleys or dream of exploring the icy oceans of distant moons. The very notion of home will expand, not to replace Earth, but to honor it by ensuring that its legacy endures among the stars. As we stand at the edge of this new horizon, one truth becomes clear. The journey to Mars is not about escaping Earth. It is about fulfilling the destiny that curiosity, intelligence, and imagination have carved into our DNA. We are explorers by nature, builders by necessity, and dreamers by design. Mars is simply the next step in a journey that began when the first humans looked up and dared to wonder. Thank you for joining this exploration, for imagining the future with an open mind and a courageous heart. Your curiosity fuels the spirit of discovery that will carry us forward. And as always, thank you for watching.